Hello, hello. I'm really glad to join the Cyberthon and to be here. My name is Marijus Briedis. I'm the CTO of NordVPN, one of the biggest B2C VPN providers in the world. And I'm really happy to see that these events are happening in Lithuania right now. And I hope that all the guys that are participating in this are gonna have a really good time. So good luck and have fun for you. But continue a little bit about me. I'm part of Nord Security Group. We are working in cyberspace with our different products. That is NordPass, NordBlocker, and as I mentioned, NordVPN. And the main areas that I'm interested in are networking, DevOps, SRE, people dev, cybersecurity, of course, and crypto. So the main questions that I'm tackling right now, how does the theory of quantum mechanics can change the computation, and how does it not change it, and what problems we are still having and harder for quantum computers, and how does quantum mechanics change the cryptography. That is the main reason that I am today. I would like to share you the information that I had about the state of post-quantum cryptographic algorithms, and what is the state in general, where are we now, what is the adoption, and what research types are popular in quantum crypto. So let's jump back into agenda a little bit. When I was preparing for this presentation, I asked around my friends, what do they know about quantum computers, the theory and the practical side of stuff, and I figured out that there is not much. So I decided to introduce and to have a little bit of history about quantum computers in these slides. After that, we're going to talk about the NIST reaction and the problems that were tackled, and a little bit about the adoption, about the software, what we have today with the quantum crypto and possibilities in there. So going into the history, please take a note that this is basically my opinion about all the events that are really important and happened. There are a lot of them, especially in the last year or 2 years ago. Quantum computing space is really changing rapidly. So going into the 80s, for the first time, Paul proposed the quantum mechanical model for the Turing machine. And year after that, Richard Feynman joined with a new paper and theory that was published. Basically, he suggested that quantum computer have the potential to simulate things that a classical computer could not. And his main interest there was to tackle the quantum physics problems. He believed that quantum computers can help in this field too. In '85, David started working on the first quantum algorithms, and it was a really interesting field for him too. Basically, if you're going to talk with the post-quantum cryptographers and quantum computer scientists right now, they do believe that these guys, Feynman and David, are the fathers of the quantum era in general. So after 7 years, in '92, there is a Deutsche algorithm. This is basically the first example of quantum algorithm that is exponentially faster than any possible deterministic classical algorithm. And after that, 2 years, Shores comes with a really great development of the algorithm for factoring integers and has the potential to decrypt the RSA encrypted communications. His work is based on the paper that was published in '93, and he worked really hard for 1 year on this, and for the first time showed that we can basically find the factoring integers in the quantum space. In general, this is only the theoretical papers and mathematicians trying to solve the problems, and one of the examples that I can talk is, you can imagine the archipelago, for example, with thousands of islands connected by bridges, and you're looking for a route that crosses each island only once, and assuming you have a million possibilities of routes and only one correct, the classical computer here would take about 500,000 attempts on average to find the right solution. And these guys try to tackle this with quantum computers in concert and saying that the problem can be solved in only 1,000 attempts. This is basically 500 times faster. There are a lot of papers that I'm not mentioning here right now, but take a look on Wikipedia, there are a lot. And then 20 years later, Edward Snowden joins and says and confirms that NSA basically has the project for penetrating hard targets. and seeks to develop a quantum computing capability for crypto purposes. What does that mean? I leave it for your imagination. But 3 years later, Microsoft really reveals its Q#. It's a programming language integrated into Visual Studio, and programs can be executed locally for 32-qubit simulator and 40-qubit simulator on Azure. The same year, IBM reveals that they are working on 50-qubit quantum computer that can maintain its quantum state for 90 microseconds. That's really a big achievement for them too. We jumped 1 year later. Google announces the creation of the Bristol cone, the first 72 quantum chip that they are working. And the same year, USA sees that a lot of private companies are going into this field, and they decided to join. Donald Trump signs the National Quantum Initiative Act and says that for the 10 years, upcoming 10 years, we want to accelerate and develop quantum information science in general, and to see the technology applications for the USA. Then a little magic happens in 2019. Google claims that they reached quantum supremacy with its Sycamore, another 54-qubit computer. Well, they used 53 because one was kind of out of order. And the same year, IBM reveals that they too have a quantum computer of 53 qubits. Only yesterday, I checked what's the recent news and found out that Chinese are on these problems too. They say that they achieved the processing power of 76 qubits. That was 10 billion times faster than Sycamore, and that is really amazing. But the main point here that I would like for you to share, that if we in 80s and 90s tackled the theoretical problems, now we are in the experimental field, and we are trying to solve what was written then. And the possibilities are really great. If you're going to look in these people who worked on these quantum theories, they are now working on and writing papers on another ones, for example, of quantum copy protection software and quantum money, that it's impossible to falsify. But there are some challenges too with this. One of this example is this slide and what is happening in quantum computing era in our crypto. So the need and uprise for post-quantum cryptography is kind of clear, because as we can see in our field right now, we have public key crypto that is RSA or SEC or Diffie-Hellman based, and they all have difficulty of factoring. It's a discrete logarithm problem or difficulty factory problem, it doesn't matter, but they can be solved theoretically efficiently in quantum computing era. Symmetric keys and hashes are a little bit better, but they need larger keys and longer outputs due to the Grover's algorithm, because it basically cuts down the computation by half or by 3 times when dealing with these problems. So NIST basically has to react. NIST, being the biggest blue team in the world, launches in 2016 the post-quantum crypto standardization project and says, hey guys, we need some ideas how to have a post-quantum secure world for our cryptography. And the mere goal is to standardize the post-quantum public key crypto, including encryption, signatures, and key encapsulation. So 1 year later, we hit the deadline for submissions, and we have 69 candidates algorithms for that, as they say in their paper, that met both the minimum acceptance criteria and submission requirements. The first round lasted for one year again until 2019 January, and this time we have 26 algorithms that advanced the second round, and they should be investigated for more analysis. What is happening right here is really interesting, because currently post-quantum crypto research is mostly based and focused in 6 different approaches. It's lattice-based, multivariate-based, hash-based, code-based, and super singular isonic crypto-based. And there's, of course, quantum resistant and symmetric key. But if you see the slide, you can tell that most of them are lattice-based that advance to the second round. There are some multivariates and cos-based variants too. For me, it's really funny to see because all these new crypto algorithms have their special names and they have their own special websites. And I'm always joking around that instead of logos, they should have only an Instagram accounts and Facebook pages missing. So the goal is to spread out the news that people are working here and to share the code too, that people could look at it. But after the second round last year in July, finally we have the finalists and alternative algorithms. So in the third round finalists, we have a public key encryption camps for key exchange mechanisms, that is Macaulay, Crystal, Interview, and Saber. And digital signatures should be done with Crystal, Falcon, and Rainbow. And you can see in the finalist round, we see a lot of lattice-based cryptography too, one multivariant and one code-based thing. And of course, NIST wants to be secure and sure. If they're going to find, for example, some problems in lattice crypto, they could jump just to alternative candidates and use something from there. So they say that, okay, we have the finalists. We are pretty sure that one of them going to be standardized in upcoming year or so. But we have an alternate candidates too. They are pretty good too. If you're gonna create an algorithm and you wanna participate in this kind of standardization with NIST, you have to keep in mind that you have to make sure of three criteria. One is, of course, the security. The second one is cost and performance, and the third one is the algorithm itself and its implementations. Looking back to the second round, when I was reading the paper, I saw that a lot of algorithms had really a lot of problems with cost and performance because what we have with our discrete algorithms, the keys are really small, and it's really easy for our CPUs and phones to deal with them. But in post-quantum algorithms, we have a little bit bigger keys, sometimes even 10 or 20 times bigger. So what NIST are saying right now, that between 22 and 24, the recommendation will be out, and one of these will be standardized, that we had the exception with IAS2. So what about the adoption? For me, this is the most interesting question. Can we use it right now? Are there any software today to experiment for us to put into our products, or even for people at their homes to experiment and to see the code or maybe see the mathematics behind it? And the good question is yes, there are a lot of usable software out there, especially that, and I'm really happy to see that most of the algorithms are really open sourced, as I mentioned before. OpenSSH guys were the first ones to jump into post-quantum keys. In 7 version and 8 version, they added PQ6 MMS keys and Interview. Later, about a year or so, they updated the Interview algorithm keys too. That was really nice. The most exciting project for me, of course, is Open Quantum Safe project that has its own library that is called libOQS. It's open source, written in C, and you can find almost all quantum-resistant crypto algorithms there. There are prototypes and integrations into protocols and applications, including the widely used OpenSSL. So when we look at the TLS section, we can see that they have their own forked OQS OpenSSL version, OQS Boring SSL if you like it better, and there is even the engine for your implementations too. For SSH, they have their own OpenSSH version 2 forked. You can try it even today. For the certificate section, you can use the same OQS OpenSSL and derive the keys and play with them. For CMS and SMIME, the same OpenSSL version. Last year, Cloudflare with Google did a really interesting experiment. Google has its own software that is written in Go and C. This is for the Go lovers. You can find it on GitHub. It's called SoakCL. They also implemented a lot of finalists and alternative algorithms that are approved by NIST already. And with Google, they kind of pushed to the edge of their cloud and tested how good they are. So the results are there on the blog site. I encourage you to read about it too. So from my point of view, I'm using StrongSpan with NTRU. I'm really happy about it already. For my own purposes, of course, we don't use it in production, but we are really looking into the field and really happy to see that there are a lot of new things upcoming every year. The next question would be, of course, what is the next 10 years going to look like in quantum computers and quantum crypto? So all of the stuff that I mentioned, it's a little bit scary maybe for somebody that doesn't understand how quantum computers works in general, but useful quantum error correction is basically the biggest problem right now for the guys. They can do the math, for example, that quantum supremacy that I mentioned earlier by Google, but they need supercomputers to really prove the math too. And only Chinese guys last December proved that they can replicate the Google results of quantum supremacy. So I think in the next 10 years, we're going to see more of that. I think that we're going to see more of simulations of quantum physics too. Quantum gravity is really interesting, another topic. And as I mentioned, error correction is a really big problem that guys are trying to tackle right now. So that's a really short and presentation for me. We can jump back. If you guys have any questions, please let me know. If not, you can always write me an email to discuss, especially about crypto or cybersecurity in general. I would be happy to answer you.